Hello. So on the screen before you now, we have Lagrange's sum of cosines identity, and the plan for today is that we should be deriving it. So I got this problem, or well, I've been inspired by Michael Penn's video on the same derivation, but I'm using a completely different method to what he does. He uses a lot more complex analysis. I'm going to keep it a bit more, how would I say it? I'm just using other identities, well-known facts, and then a bunch of algebraic simplification at the end. Right, without further ado, so this sum here then, this is going to take the form of, like, if we just think about what it is, this is going to be 1 plus cosine of theta plus cosine of 2 theta plus cosine of 3 theta, etc., etc., all the way up to cosine of n theta. And oops, let me go down a bit. What we want to do is find a closed form for this expression. But to do that, well, if you're ever trying to sum and work with a bunch of trigonometric functions like this, you're not going to have a good time. So what we're going to do instead is use the fact that cosine is related to the exponential, using the identity cosine of theta equals e to the I theta plus e to the negative I theta over 2. We're going to use this fact to make it, instead of summing a bunch of trigonometric functions, we're instead going to be summing exponential functions. And we can just, so in our original problem, you've got an n up here. Because it's the input of the cosine, we can literally just add an n here, and this is still true. Perfect. Alright, so let's substitute this into the sum then. So this is equal to the sum from n equals 0 to n of e to the I theta n plus e to the negative I theta n all over 2. And I'm going to separate this. I'm going to factor out the 1/2, and I'll separate this into two different sums to make it easier to work with. So okay, so looking at this, you might say, well, look, I haven't made it any easier. Like, surely instead of working, before we had nice familiar cosine functions, and now we've got I up in here, we've got this exponential function, like, it's not looking good. But let me make a substitution and we'll see if that makes it clear why this is useful. So if we set u equals e to the I theta, because it's quite confusing having these e to the I thetas hanging around everywhere. Now we have the sum 1/2 times the sum from n equals 0 to n of just simply u to the n. And as for the other one, that is plus the sum from n equals 0 to n of u to the negative 1 to the n. And if you have any familiarity with series at all, you know these two are geometric series. And in fact, we have a nice simple formula to get a closed form for these. So this is equal to 1/2 times u to the n plus 1, capital N, minus 1, over u minus 1, plus u to the negative n minus 1, minus 1. How many times am I going to say minus 1? U to the minus 1 minus 1. And there we go. So now we've got it in the closed form now, which is nice. Like, honestly, what we could really do here, substitute back in e to the I theta and say that we're done. But this isn't exactly the very nice form we had it in earlier. So what we will do instead of that is a whole bunch of algebraic manipulation starting with combining these two fractions. So what we can see here is that if we times by negative u on the top and the bottom, we have the same denominator of u minus 1. So I will quickly do that. And then I will combine the numerators. So this gives us 1/2 u to the n plus 1 minus 1 minus, and then so we have u times u to the negative n minus 1. That will just give us minus u to the negative n. And then minus 1 times negative u, that will give us plus u. Alrighty, and on the denominator we have u minus 1. Okay, and I'm going to group these terms. So we can see we have a u minus 1 on the top here and a u minus 1 on the bottom. So what we can actually do is re-separate into two different fractions again, and we'll have 1 plus another fraction. So I'll do that. That'll give us 1/2 of 1 plus, and then the remaining terms in the numerator, u to the n plus 1 minus u to the minus n on u minus 1. Perfect. Okay, and the last step, now I think this is the most unintuitive step in the whole thing, to be honest. And what we're going to do is we're going to multiply the top and the bottom by u to the negative 1/2. Okay, and you might say, well, look, u just times by the reciprocal of the square root of u. How is that going to help? And I say, you will see, because if we think of these, if we think of this 1 as being u to the 0 and this is u to the 1, well, we're going to have two, we're going to have exponents kind of matching then. We're going to have u to the half, u to the negative 1/2. I'll just write this out quickly, if that will make it easier to see. So this is equal to 1/2, 1 plus, and then subtracting 1/2 from that, we have u to the n plus 1/2 plus u to the negative n plus 1/2 all over u to the 1/2 minus u to, oh sorry, this should have been a minus. Let me correct that. U to the negative 1/2. And this is ideal because anyone, again, who is familiar with a tiny bit of maybe complex analysis will know that sine of theta is equal to e to the I theta minus e to the negative I theta all over 2i, and this is exactly kind of the setup we have here, except obviously without this 2i, but that's fine because we can multiply by 2i. So 2i sine theta, that will be equal to e to the I theta minus e to the negative I theta, and the importance of this is that these exponents are now like matching but negative. So we can resubstitute, instead of, because we know u is e to the I theta, we can resubstitute with signs. So this will give us 1/2, 1 plus, okay, and for this top one, well, we're going to have a 2i there, and then times the sine, and just got to figure out what the input is. So you've got n plus 1/2, and then also the theta from the u being e to the I theta. So that is n plus 1/2 theta. And we are almost done. So we have then on the bottom again 2i times sine of, and just the 1/2 instead of the n plus 1/2, sine of 1/2 theta. And there we have it. So we can cancel these two i's from the top and the bottom, and we have all basically just derived the identity. So if we go back a bit, all we have to do is distribute this 1/2, leaving us with 1/2 plus sine of plus 1/2 theta on sine of 1/2 theta. Thank you very much for watching. Please check out the original video, which no doubt you've probably seen, of Michael Penn deriving this. He, instead of using the facts, he used a very similar fact. I used up here somewhere that cosine of theta is equal to e to the I theta plus e to the negative 5 theta all over 2. He used that cosine of theta is the real part of e to the I theta, and used some fancy facts about linear operators or something silly like that. But clearly got the superior method here. Thank you very much for watching.